Welcome to Fear the Engineer, where I explain engineering topics better than your professor. Let's learn about uniform circular motion. Circular motion occurs when a particle travels along a circular path. Uniform circular motion occurs when that particle travels with a constant speed. We need three things to describe the particle's motion: position, velocity, and acceleration. Let's start by looking at position. We need two pieces of info to describe it. First, we need to know the particle's distance from the center of the circle. This distance equals the radius r of the circle, and it remains constant. Second, we need to know the particle's angle compared to some reference. This is called theta, which is the angular position. We usually use the horizontal axis as the reference, and theta is positive if the angle is counterclockwise from that reference. Theta's units are usually in radians, but we can use degrees or revolutions. To convert, just know that 2 pi radians equals 360 degrees, which equals 1 revolution. If we multiply the radius and the angular position together, we get the arc length, s. This tells us how far we have to travel along the circle to get to the particle, starting from some reference point. Once again, we use the horizontal axis as the reference. To use this formula, you need to have the angular position in radians, not degrees, so keep that in mind. Now, let's look at velocity. We'll start with angular velocity, the rate of change of the particle's angular position. It tells us how quickly the particle's angle is changing, and in what direction. We represent this rate of change with the variable omega. We can find it by taking the derivative of theta with respect to time. This is the same thing as looking at the slope of the theta versus time graph. Since we have uniform motion, the particle is circling with a constant speed. This means that the rate of change of the angular position is constant. So omega is constant. Its units are usually radians per second, but you can also have it in degrees per second or revolutions per second. Angular velocity has a magnitude and a direction. The magnitude tells us how quickly the particle's angle is changing. We call this the angular speed. It equals the particle's change in angle divided by the change in time. If the particle completes a revolution, its angle changes by 360 degrees, or 2 pi radians. We can divide that by the time the particle takes to complete a revolution, which is called the period, t. That gives us the angular speed in radians per second. We can also calculate the angular speed if we know the particle's angular position at two different times. We just subtract the initial angle from the final angle, and then we divide by the difference in time. Then, we take the absolute value. The direction of the angular velocity tells us which way the particle is circling. It's either clockwise or counterclockwise. Usually, we write clockwise angular velocities as negative, and counterclockwise angular velocities as positive. This is just a common convention. The problems that you'll be dealing with will probably tell you the direction. You can also determine it by comparing an initial angle with a final angle. One more thing. Since omega is the derivative of theta, we can solve for theta by integrating omega. If we integrate omega from an initial time to a final time, we get the difference between the initial theta and the final theta. This is also called the angular displacement. Then, we can rearrange to solve for the final theta. This comes from the Fundamental Theorem of Calculus. Check out the link in the description for a refresher on it. Also, remember that integrating is the same thing as finding the area under the curve. So the final angle equals the initial angle plus the area under the omega versus time curve, from the initial time to the final time. Omega is usually a constant, so that area is just a rectangle. It has a constant height of omega, and its width is the difference between the initial and the final times, which we call delta t. Now, let's look at tangential velocity. This is the rate of change of the particle's distance along the circle. That distance is called the arc length, s, which we mentioned earlier. To find its rate of change, we just take its derivative with respect to time. That gives us the velocity of the particle along its arc. When a particle travels on an arc, its velocity is always tangent to the arc, as you can see in the diagram. That's why we call this the tangential velocity. Let's take the derivative. We know that s equals r times theta. R is a constant, so the derivative is just r times the derivative of theta. The derivative of theta is omega, the angular velocity. so the tangential velocity equals r times omega. Since we have uniform motion, omega is constant, so the tangential velocity is constant too. To use this formula, make sure you have omega in radians per second. Notice how the radius affects this velocity. If two particles are circling with the same angular speed, like 90 degrees per second, the particle that travels around a circle with a big radius will have a much faster tangential velocity than the one traveling around a circle with a small radius. This is why it's harder to run on the outside lanes of a running track rather than the inner lanes. The tangential velocity has a magnitude and a direction. The magnitude tells us how quickly the particle is moving. We call this the tangential speed. We can find it by multiplying the magnitude of omega by the radius. One equation for the magnitude of omega is 2 pi over t. If we plug that in, we get 2 pi over t times r. Check out the numerator. 2 pi r is the circumference, the distance around the circle. So this first formula says that speed equals the distance around the circle divided by the time the particle takes to travel around it. This makes sense. Speed equals distance over time. We can also use the other equation for the magnitude of omega. This one divides the change in angular position by the change in time. Then it takes the absolute value. All we have to do is multiply that expression by the radius. That's it for magnitude. The direction of the tangential velocity tells us which way the particle is moving. It's either clockwise or counterclockwise. Usually, we write clockwise tangential velocities as negative and counterclockwise ones as positive. This is just a common convention. By the way, I'd really appreciate it if you could give me some quick feedback to help me improve. The link in the description takes you to a Google survey that takes less than a minute. Now, let's look at acceleration. For uniform circular motion, the acceleration's direction is toward the center of the circle. We call it the centripetal acceleration. Centripetal just means center-seeking. But why does the acceleration point toward the center? Well, we know that acceleration is the change in velocity over time. This change can come from the magnitude of velocity or the direction of the velocity. The magnitude of the velocity is constant because we have uniform motion. The speed doesn't change, but the direction of the velocity is changing. And if we look at that change, we'll see that it's pointing toward the center. We can visualize the change in the direction of velocity by comparing the particle's velocity at two similar locations. Here's the first, and here's the second. To get the change in velocity, we can draw a vector from the end of the first velocity vector to the end of the second one. Clearly, the change from the first to the second velocity is pointing approximately perpendicular to both of those velocities. I drew that acceleration vector in a spot that's easy to see, but it really acts on the particle as it moves between those positions. If I move the vector there, we clearly see that it points toward the center of the circle. Acceleration has magnitude and direction. We just looked at direction, but what about magnitude? It equals the tangential velocity squared divided by the radius. We can get another expression for the magnitude by replacing tangential velocity with its formula, omega times r. That gives us omega squared times r squared on the numerator divided by r. We can cancel out an r term to get omega squared times r. Make sure that omega is in radians per second. But how did we know that the acceleration equals tangential velocity squared over r? You probably won't be tested on this, but here's the explanation. We know that acceleration is the rate of change of velocity, so we need to take the derivative of the velocity. That gives us dv over dt. We're going to need to replace the numerator and the denominator. Let's start with the denominator, dt. We know that the expression for velocity is r times d theta over dt. We can rearrange and solve for dt. This gives us r times d theta over v. Now we can plug that in. Now let's look at the numerator, dv. This represents the vector between the particle's velocities at two similar locations. This is the vector I drew earlier on the diagram. As you can see, it forms a triangle, with the first velocity and the second velocity as the sides. Let's redraw that. We're going to compare velocities at two locations that are really close together. That means that the velocities both have pretty much the exact same starting point. The angle between them is also very small, and we'll call it d theta. The vector that spans the gap between these velocities is dv. dv is the base of this triangle. The sides of the triangle are the velocity vectors. Since the magnitude of velocity is constant for uniform motion, the length of these vectors are equal. That means that we have an isosceles triangle, and we want to solve for the length of the base. Let's redraw the triangle with easier symbols. The best way to solve for the length of the base is to cut the triangle in half. Now we have a right triangle. We know the hypotenuse, we know an angle, and we want the length of the side that's opposite from the angle. We can solve using the sine function. Our angle is really small, so we can use the small angle approximation, which says that the sine of a small angle is approximately equal to the angle. That lets us replace sine of theta over 2 with theta over 2. When we solve, we find that x is approximately equal to the length of one of the sides times the angle. That means dv is approximately equal to the velocity times d theta. Now we can plug that into the numerator. When we simplify the expression, the d theta terms cancel, and we get v squared over r. Here's a summary of the formulas we can work with when dealing with uniform circular motion. We just finished learning the concepts. Nice work! In the next video, we'll practice our skills with some practice problems. If you liked the video, you can thank me by giving me some quick feedback to help me improve. Just click the link in the description to fill out a quick 1-minute Google survey. If you found this video helpful, subscribe to get notified when I release new content. As always, keep at it and crush the course.